So from 1.3, when we're talking about compound interest, there's a few things we want to make sure that we're on the same page with, and that is how many compounding periods there are, how to calculate that, and also to take a look at this little I, right? The lowercase I, which is this, the interest rate per compounding period. Okay, there we go, thank you. So the little I is the interest rate per compounding period. Now, as I mentioned yesterday, that compound interest is interest on your principal plus all the interest you've earned so far. So it's a powerful thing. But when it's compounded more than once a year, then the annual interest rate gets divided up. So if it's compounded semi-annually, let's say, that's 2 times a year. So the interest rate, which would be 10.2, okay, if it's compounded semi-annually, like in the first part here, then the little I is 10.2 divided by 2, okay, because it's 2 times per year. So the interest rate of 5.1% is calculated every 6 months, okay? So it's divided up. It's not 10% every 6 months. If it's monthly, it's not the full annual interest rate every month. No, it's divided up. So there's 2 parts here to number 1 on this chart, and I'll just zoom in a little bit here so we can maybe... 1.3? This should be 1.3. Is it not? This is...
I just did 1.2 yesterday.
Oh, okay. All right. Okay, now we're on the same... Yes, this is 1.3, and the interest rate per compounding period is always divided by the number of times it's compounded per month. The number of compounding periods, okay, so now this is... how many times is the interest calculated over the entire term? So the number of compounding periods is always, you know, if it's 2 times per year, then it's the years times 2. Or if it's monthly, okay, for this one, if it's monthly for 6 years, it's 6 times 12, right? So 2 times a year for 4 years, there's 8 compounding periods, that's n. For the second one, the interest rate is 4.1, so the little I, interest rate per compounding period, is going to be this interest rate divided by 12. 4.1 divided by 12. Okay? And of course, I'm not going to do all these for you, but I'll just I'll get you started here. So 4.1 divided by 12, that's roughly 1/3, isn't it? It's going to be pretty close to 1/3. So let's do 4.1 divided by 12. Is 0.342, okay, or 3.4% roughly. So I think in percent is fine. 1 to a tenth is fine. So that's 3.4% 0.3%. My bad. Let's go back here. So 4.1 is 0.34 because this is percent. So this is percent. So we're not going to change that decimal at all. So 0.34%. Yeah, 2 decimal places would be good for this one because we don't have any numbers in front. But so 0.3 or 0.34%, that's every month, okay? And then the compounding periods, as I mentioned before, 6 times 12, okay, which is 72. So 6 years times monthly, that's 12 times per year. Question?
For the last one.
Yeah.
It says daily for 9 months. How do you do that?
Yeah, daily for 9 months. Okay. That's yeah. Let's do that one. Let's skip to this one because so daily is 365 per year, right? So how many days are in 9 months? Well, that would depend on the number of months, you would think, right? Right? Remember the whole January, February, March, April, the 31. So you're not supposed to do that because you don't have enough information for that. Instead what you do is you go 9 out of 12 times 365. That would be how you do that. Or if you're given weeks, like let's say you're given 37 weeks compounded daily, okay, well you go 37 over 52, that fraction of a full year, times 365. So in this case, 9 months would be 3/4 of a year. So you'd go 3/4 of 365 days, and that's how many days. Okay, now you can check the back of the book with this one, see if they're doing it the same way. But let me do 3.5%. So 3.5 divided by 365, because this is the daily percent, so it's really, really small. 0.0096, let's say. 0096. And then the number of compounding periods would be this right here. 9/12, because it's 9 out of a full year would be 12 times 365. So 9 times 365 divided by 12. 273.75. 273, I don't know what decimal place they want you to go to. 273.75 or 274, you can round it probably. So that's how many days, roughly, okay? All right, let's take a look at number 3 then, because number 3 has this rule of 72, which we'll go over. I don't think we did that yesterday in class. Maybe you did study that already, but I'll go over that real quick. So for this one, it says, for each investment, use the rule of 72 to estimate the doubling time and then determine the doubling time, okay? So estimate the doubling time. That's what the rule of 72 is. It's a simple formula, the rule of 72, and what you do is you take 72 and you divide it by the annual interest rate, okay? So the annual interest rate is down here, and this answer, this solution that you get over here, will be the amount of time in years that it would take to double your investment, okay? So this is the time in years.
Going to be just the amount of periods because it's not always a year. Like,
Yeah, no, it's not periods because this rule of 72 only works for annual interest rate. So this is annual, okay? It only works for annual interest rate. And it will give you the time in years that it would take roughly, this is pretty close, but roughly the amount of time it would take in years to double your investment. So this is just it's a little shortcut just for a specific situation. So let's say you had $7,000 and you wanted to know how long it would take to double it, okay? Well, you would put your annual interest rate, whatever that is, and you do 72 divided by that annual interest rate, and then you would get the time in years it would take to double that, okay? So that's what the rule of 72 is. So the interest rate is as a percent as well, okay? And so that's what you do. Now, for number 3, okay, use the rule of 72 to estimate the doubling time, then determine the doubling time. Okay, now determining the doubling time, I'm going to show you how to solve for n here, okay? I'm going to show you how to solve for n, because right now it's just kind of guess and check, really. I'm going to show you how to use logarithms to solve for n. So let's do a. Okay, so I'm going to move this over now. All right. So A here, I have $7,000 at 6.8%, and I want to know how long it's going to take to double that. Use your rule of 72. Okay, so doubling time is your 72, and it doesn't matter what the principal is. It doesn't matter. It's just what the annual interest rate is. So 72 divided by 6.8. 72 divided by 6.8 is 10.6 or so. So 10.6 years is your doubling time. Okay. Now, to find the actual doubling time, okay, so to determine the actual doubling time, you're gonna need to solve for n here, it looks like, okay, because we need to find, this is the number of periods. So if it's annually, that's going to be years, right? If it's monthly, that's going to be months. If it's semi-annually, it's going to be 0.5 years, how many 0.5 years it's going to take. So this, and again, I look back in the textbook here, and it doesn't deal with logs at all. I don't know. I can't find an example. So I'm going to show you how to use the logs here to find this. So for B, or for a second part, I guess, of number 1, determining the doubling time. So my principal here for A is 7,000. Okay, so the principal is 7,000. The A, remember, is future value. Future value. So the future value, I want this to be doubled. So that's got to be 14,000. So we're going to actually solve for n here, but we have to put in all the appropriate numbers here. So 7,000 is going to turn into 14,000, and I need to know how many compounding periods that's going to take. So I need to solve for n. So this one is compounded annually, so that's great. This little I would be the percentage per compounding period, which is the same as this percent. So 1 plus, and it's the decimal form of this percent divided by 1. So 0.068 to the power of n. So n is what we need to solve for here. All right. Which up to this point, I don't think you've done an example or a question like that. Nobody's run into this, right? And if you have, I think the only thing that I can see is that you basically just guess and check to the nearest decimal place what n might be. So let's go over the math here to do this. So what we want to do is we want to obviously isolate for n. So we're going to try and isolate first of all for this part. So we want to get this all by itself on the one side. So we're going to divide both sides by 7,000. Okay. So this is going to be 2 over here equals 7,000. And this is going to be 1.068 to the power of n. Okay. So how many times do I have to multiply 1.068 times itself to get 2 exactly? Well, you could guess and check here. Wouldn't take you a few minutes to get to a real accurate number. But the way you do this is using logarithms, okay? And if you took Pre-Calculus 30, you would have learned how to do this. If you haven't taken Pre-Calculus 30, this is probably new to you. So we take the logarithm, and you'll see a log button on your calculator. We take the logarithm of both sides. So this log button, that's the logarithm. And the logarithm is very handy in solving for exponents, okay? So this is how we bring the exponent out of the exponent position in order to isolate it. There's no other way you can do that. You can't divide or add or subtract, or you could take the nth root maybe of both, but you don't know what's the nth root of 2. Well, you don't know what n is, so you can't solve for n, right, that way. The only way we can do this is with logs, right? So what's the special property of logarithms? Well, let me show you this. You might want to write this down. Log, and again, the base here is just going to be common base of 10, so we don't have to write that down. It's base 10. But
Mr. Webb, please call 220.
if you have the log of x to the power of n here, that can be written as n times log of x. This exponent can literally be brought down as a coefficient that is multiplied. Okay, it's the exact same. It's just the way that works. Okay, the logarithm is an exponent. It kind of undoes to the power of. So how do we undo to the power of? We use logarithms to do that. So this is going to be very handy for us because the next step is going to look like this. Log of 2 equals n times log of 1.068. I won't get into any more what logarithms mean. That's another course, so I'm not going to teach you that today. But I will show you how to use your calculator and how to solve for this, okay? So now we've got n just as a regular multiplier here. That's excellent. Now we can use standard algebraic methods to isolate for n. And I'm going to divide by log of 1.068. I'm going to do that from both sides. So that now this factor is gone with this one. And I have just n all by itself here. And on your calculator, this is pretty straightforward to do. All right. Turn your calculator on, that'd be a good idea. So you go log 2, finish your brackets there, and divide by log, just use your log button, 1.068. Okay. And you get an answer of 10.54. So we'll say 10.5. Well, okay, 10.5. Now look at our rule of 72 estimation was 10.6, right? And we might have even, I don't have it on there, might have even rounded that a bit. So 10.5 versus 10.6 is pretty close, pretty good estimation. Now again, this is annually, right? So the n is years. If the interest rate was compounded monthly, n would be the number of months, okay? If it's compounded quarterly, you'll see that too. That's 4 times per year. That's every 3 months. So the n would be groups of 3 months. Okay, so you have to interpret n. And this is 10.5 years. Yeah, question.
Because it's done annually, don't, like.
Because it's done what, sorry?
Because it's done annually.
Yep.
Doesn't that mean that it needs to be either 11 or 10 years? Because.
No.
Like, if it can't be 10.5 years because it doesn't pay it back at 10.5.
Yeah, yeah, I think you can stick with this. We're just looking for the amount of time that it would take, to double. I understand what you're saying. It's compounded annually, so it's calculated annually. I think you can stick with this. If it'll say in the question around to the nearest year or around to the nearest compounding period or whatever, but we won't worry about that right now. You're right. It's not going to be calculated. But see, at 11 years, you're going to have more than double, right? So 11 is misleading in that, is it going to take 11 years? No, it's not going to take quite that much technically. So yes, I see what you're saying. It's not calculated at 10.5 years. That's fine. We'll leave this for our answer, I think. Yep.
If it's not annually for the equation, would you like have to do a different interest? Like
Yep. Yeah, exactly. If it's not annually, then this interest is not going to be the annual interest. Yeah. Okay, so that's what we talked about up here, right? So if it's monthly, right, then you take this and you divide that by 12, and that's the interest rate, which I thought I had that up here. I think it disappeared on me. So 4 divided by 12, what was that? 0.34%, I think. So this is the I in the equation, yeah, and then the n that you determine is going to be the number of months. Okay? All right, that's 1 and 3. That's rule of 72 for 1.3. Any questions on those ones?